In the previous part of our two-part episodes on logarithmic differentiation, we looked at and finished with the idea of taking the derivative of the inverses of functions that don't have an obvious inverse and whose inverses are non-elementary functions, such as this Lambert W function, one of my favorite functions personally. And we showed this using logarithmic differentiation and operators in general. And so we got this answer. And so that's just one of the examples of how awesome not just implicit differentiation is, but namely logarithmic differentiation. And what we're going to do in this video is find out and do a little bit of fun with logarithmic differentiation so that we can even answer the question of something like, what's the derivative with respect to x of the Lambert W function raised to the Lambert W function? So that's something you should be able to do at the end of today's episode. So let's go and look at something very cool. What we're going to do today with logarithmic differentiation is find the derivative of some function f of x raised to the power of some other function g of x. And so how are we going to do this? Well, remember from the last part that logarithmic differentiation takes into account two key ideas. The first being the chain rule, okay? So the first big idea here is the chain rule. And the chain rule rules, okay? It's the reason why this is all possible. All right, because when you take the derivative of the logarithm of some function, or the logarithmic derivative as it's called, so d dx of the log of f, then we get something called the related rate of f, which is going to be f prime over f. All right, and you can intuit why such a ratio would be so important in so many different situations. And so that's the reason why the chain rule is so important here. The other idea is the language of operators and operator algebra, because we apply the logarithm operator to both sides of the equation in order to then take the derivative operator of that equation. So let's start with this idea here. Let's just say that f of x is equal to f. So we have f equals f of x, like this. And then g equals g of x, just as a shorthand so that we don't have to do as much writing. All right, so we're going to find the derivative with respect to x of f to the g, okay? Looking like this. All right, so what we're going to do is we're going to set y, our function, equal to f to the g, okay? F of x to the power of g of x, which means we want to show, or want to find, WTF, want to find, mind you, dy dx, okay? So what do? Well, we take the log operator, which is this big kind of, I use capital LOG for log, and that's the natural log. So you have natural log of y, or just log of y, is equal to, and by the exponent rule, the log of f to the g is the same thing as multiplying that exponent downwards. So we get g times the natural log of f, all right? And since I'm not an animal, I will put brackets around my inputs, all right? Because you're not multiplying these two things together. So anyways, now we can take the derivative, and we're going to hit it with the derivative operator. Now remember that f and g are functions in terms of x, and y is a function in terms of f and g, which is in terms of x. So we take the derivative of the left-hand side, we get 1 over y times dy dx by the chain rule, which is why it's so important here, right? Like this. And that's equal to, by the product rule here, I'm going to move this actually to the left here a bit more because we're running out of space. This is equal to f prime g plus g prime f. Well, in this case, the f prime is g, so I'm going to say a prime b plus b prime a. So here's our a, here's our b. So the product rule says a prime b plus b prime a. Well, a prime is just g prime, right? And b is going to be ln of f, okay? And then you add that, folks, to b prime a. And so a is just g. All right, what's b prime? Well, we just said that the logarithmic derivative is the relative rate, the related rate, f prime over f. So we can say it's plus f prime times g over f. And therefore, the dy dx, so the derivative of y with respect to x, is equal to itself and then some. So we get y times, here, g prime ln f, so log of f. And then we add that to this quotient here that is the related rate of f, but then you multiply that by g. So you have f prime over f here, and you multiply that by g. All right, and that's interesting because you have the related rate only as showing up as f here. Okay, so that means, therefore, that the derivative with respect to x of the function f of x to the power g of x is going to be, grand finale here, it's going to be itself, f of x to the power of g of x, and you multiply that, oops, here we go, you multiply that by g prime of x, okay, times the log of f of x, like this. So you have f of x, all right, and my brackets are kind of getting out of hand, but it's okay, plus over here, we have f prime of x times g of x, not a composition here, just mind you, g of x over here, and we divide that by f of x altogether. So this is pretty cool. We use logarithmic differentiation to define a formula for any function raised to any power, that being even in a functional power. So let's take some examples. We can do derivative with respect to x of the function x to the x. And we're going to use this formula, which we just derived, which is a bit of mathematical fun, to show that there's a lot of derivatives that can be proved with this formula. So, x to the x, what's f of x? Well, f is equal to x, right? And g is equal to x. Then f prime is equal to 1, and so is g prime. So then we can just plug these values into the formula. So the derivative should be x to the x times, well, g prime is 1, times the ln of f of x, which is ln of x, plus f prime is 1 times g of x, which is x, over f of x is x, and we get equals x to the x times log x plus 1, which is in fact the derivative, and we proved that in the last video. So that's already cool. That's one sign that this formula works for these unusual functions derivatives. How about another thing we looked at in the previous video, d dx of e to the x? In this situation, remember that the functions are only the base and the exponent. So here the base is e, so f is equal to the base, which is e, which means f prime, since e is a constant, is equal to 0. So be careful with there. And g is equal to x, okay? And then g prime then is equal to 1. So plugging it into our formula, we get that this is equal to e to the x, all right? And we multiply that by the log of f, so it's going to be ln of e. I'm going to put that in, ln of e. And you multiply that by the g prime, so we get 1. And we add that, folks, we add it to that quotient here of f prime times g over f. So f prime is 0 times g is x over f is e. So of course you can see that this entire thing goes to 0, because that's 0 over here. Ln of e is 1, all right, multiplied by 1 is 1, and we get e to the x, all right? And therefore, this formula does work for e to the x. So already, another example of what's true. We also looked at in the last video the derivative with respect to x of x to the n, for n being an element of the reals. All right, and this is the power rule. We proved it with logarithmic differentiation. And now we're going to show that this formula that we just have over here is going to work as well. So by that formula, remember, we have f is equal to x, and then g is equal to a constant. So this time g is a constant, n, which means g prime is equal to 0. And then f prime is going to be 1, all right? So this is equal to itself and then some, okay? We have the g prime times log x, which is going to be 0 times ln of x, which right away goes to 0. And we add that to the f prime times g, which is going to be x times n, or sorry, f prime g is going to be 1 times n, excuse me, over f, which is x over here. So we get nx to the n over x, which is equal to nx to the n minus 1. And there you go. So the formula does work, which means if you plug in the derivative of x squared, for example, into the above formula, you will get 2x. Or if you get x to the pi, you'll get pi x to the pi minus 1. And that's very cool. And finally, we're going to generalize a couple more ideas. So, with this formula, another insane example, and I bet you can't even graph this function on your own, but the derivative with respect to x of sine of x raised to the power of sine of x. All right? What is that equal to? Well, you can use logarithmic differentiation, of course, but you can also use this formula that we just showed, that we just derived. So again, it's equal to itself and then some, which is a phrase I like to use because it's easy to remember. So you have sine x to the power of sine x over here. And let's be clear of what is f and what's g. So f here is sine x, but that's also g, which means that their primes are also equal. So f prime is equal to cosine x, which is equal to g prime. All right, so we have this is equal to sine x to the power of sine x, and I'm gonna move this down so it's a little less confusing. There you go. It's sine x to the sine x, and multiply that by the log of sine x. All right, I'm gonna switch colors here real quick. The log of sine x, and we multiply that by g prime, which is cosine. All right, so times cosine, and we add that to that difference quotient, or not the difference quotient, but that related rate, and then times the original g function. So what's f prime on top? It's cosine x, right? And what's g? Well, g is just sine x. So we have cosine x times sine x, and we divide that by the original f, right, which is sine x. So of course you can see here that the signs cancel. And so we can factor out the cosine here, right? This cosine over here can also be factored out. And so what we get is ultimately the derivative with respect to x of sine x to the power of sine x is equal to, factoring out the cosine, we get cosine of x times sine x to the sine x power. And we multiply that by log of sine of x, right? Like this. And we add 1. Now, this might remind you of something. This ln of something plus 1 and then itself reminds me a little bit personally of the derivative of x to the x, which is x to the x times log x plus 1. And in fact, if you have an x prime in here, you have the derivative of x is 1, so it's kind of like 1 times x to the x times the log of x plus 1. Okay? So there is possibly a special connection when these two functions are the same. And this leads us to a corollary of this formula. Okay? So I'm going to reproduce this formula down here because we can then introduce a corollary, which is sort of just saying like an additional statement that is proved or derived as a subsection of the main statement. So if f equals g, right, then the derivative of f to the f with respect to x, like this, is equal to, well, we have f to the f by that formula, times f prime log of f prime, and we add that to f prime times f over f, right, because these are equal, which means we can cancel out the f's over here and factor out the f prime, and so the derivative with respect to x of f of x to the power f of x, so it's that function f to its own power, to its self power, is equal to the derivative of f, so it's f prime of x, times f of x to the power of f of x, and then we multiply that by 1 plus the natural log of the function f of x. And if you plug the x to the x formula, or the derivative and functions into this, you'll get that answer. So you can tell me also with the sine of x to the sine of x power that this is also true. So that's another cool corollary. So I'm gonna circle this here. I'm gonna say this is the corollary. Okay? Right there. Okay. Now, there is another interesting thing to do. There's so many more interesting things to do with this formula. And you can now show on your own, independently, the function w of x, the Lambert w function, right, raised to the w of x power. All right, what is that if you take the derivative of that? And because this rule is so cool, and we just derived it from logarithmic differentiation alone, I'm going to give it a cool name, and I'm going to call it the HYPERPOWER rule, okay? Because it's not necessarily hyperpowers as in like what you might see of a repeated power like this, but it's just so ultimate and powerful that we might as well give it this cool name, HYPERPOWER rule, okay? So this is a very cool idea that we just proved, and this is the corollary to the HYPERPOWER rule, okay? Now, I want to conclude this two-part series on logarithmic differentiation with a few applications of logarithmic differentiation, because you might wonder, this is all fun and cool and all, but why is it actually useful? And if you've heard of the Richter scale with earthquakes, it measures the intensity of earthquakes with a logarithm, okay? It's a logarithmic scale, the Richter scale. And so perhaps if you wanted to see the rate of change of the Richter scale, of the intensity of the earthquake in the moment or over time, you might want to take a logarithmic derivative. Or, for example, if you've taken chemistry, you definitely know about the pH scale, okay? The pH scale, which can tell you how acidic or basic a certain solution is, or neutral if they're basically equal concentrations of H plus hydrogen ions or hydroxide OH minus ions. So this is number 7 here from 1 to 14. And if you wanted to see, for example, if you're distilling a solution, the rate of change, perhaps, of the pH of a certain solution that follows a different function over time, and it's logarithmic in base 10, you might want to take a logarithmic derivative. So these are just a few ideas and speculations as to why the logarithmic differentiation process is so important and where it's applied. So I hope that this fun video, this is more of a for fun video, guys, where we're just looking at the fun aspects of logarithmic differentiation and deriving this HYPERPOWER rule. Now remember, this will not work for many functions, but I hope you have a newfound appreciation for logarithmic differentiation and thoughts even more awesome after this video. See you next time.